Okay, welcome for this the morning session. Today, after this, the extended surfaces like fins. In that extended surfaces, you have derived the steady state heat conduction in the various cross sections of the fins. Various cross sections, maybe the triangular cross section, maybe the circular cross section, like fin, or maybe the rectangular cross section fins. Any fin, the prime motive of the fin is to convey the heat from the base surface to the atmosphere, so that the heat transfer takes place. The transfer rate can be increased by using the extended surfaces. In that extended surfaces, after deriving the general equation, we are reduce that equation into the short fin, very long fin, and the fin with the insulated tip. Like this, three conditions we are derived. According to that problems also we have solved a few problems. Uh, this the problems also you can refer any textbook. The all VTU textbook, VTU questions you must solve it by yourself. Okay, and also you should practice it yourself. The problems. Now further, I'll move on to this the one-dimensional transient heat conduction. One-dimensional transient heat conduction. The transient heat conduction is one in which the heat flow and the temperature distribution at any point of the system vary continuously with time. The heat flow and the temperature distribution vary with respect to time. That is, capital T is equal to function of x, y, z, and t. X, y, z are the coordinates, t is the time. X is the x, y, z are the coordinates, three coordinates. For one-dimensional transient heat conduction, the y and z, the z axis may be zero. That becomes the equation becomes t is equal to function of x. X means one-dimensional transient. The temperature or the heat changes with respect to x direction as well as with respect to time only. The transient heat conduction occurs in the heating and cooling of metal billets. Metal billets. As you all know that the metal billets are used for the different purposes. And cooling of IC engines. The IC engine cylinder and bore, always there may be the constant temperature at the time of running the IC engines, internal combustion engines, like the any automobile engine, like the bikes, bike cars, or maybe anything you consider it. Okay, bricks burning, and vulcanization of rubber. Vulcanization means, as you all know that vulcanizing the puncture shop. Okay, puncture shop. You are all very much aware about this the puncture shop because you are the oftenly you are visiting to the for the vulcanizing purpose of this the bikes and cars and the bicycles like that. You are all seen from the since from the childhood. Okay, this was kind of vulcanizing of rubber. The stopping and starting of various heat exchanger units in the power plants. The power plants means the lot of the equipments, heat transfer equipments will be there. In that heat exchanger is the very important equipment in the power plants. Change in temperature during the unsteady state heat transfer may be periodic or non-periodic. Means periodic variation. In this temperature changes, it's repeated in cycles. Conditions get repeated after some fixed time intervals. But the temperature, example for this temperature variation in IC engines cylinder. During the each cycle, definite variation of the temperature occurs with respect to the crank angle. This change continues as long as the engine continues to operate. The profile temperature variation with the crank angle for one cycle is called as temperature wave, and the duration of each temperature wave is called as the period. Variation of temperature of the building during the full day of 24 hours. Temperature variation of the surface of earth during the period of 24 hours. Heating process of refrigerator. Heating process of refrigerator would whose the package are alternatively heated and the by flue gases and cooled by air. Non-periodic variation, there is the temperature changes as some non-linear function of time. This variation is neither the according to the any definite pattern, or it is not nor is in the repeated cycle, such that the variation includes the process where the medium is heated or cooled by exposing to the another medium of a given thermostat. Example is the examples may be temperature changes as some non-linear function of time. This variation either according to any definite pattern or the repeated cycles, as I said. The examples of this is the heating of ingots in the furnace, and the cooling of bars, blanks, metal billets, steel, various heat treatment. The only the thing is the you don't the non-periodic, periodic, all those things. Only the thing is a transient heat conduction means the one-dimensional transient heat conduction means the temperature and heat transfer changes with respect to one axis with respect to time is called as one-dimensional transient heat conduction. Transient means it changes with respect to time is called as a transient. Okay. Every minute, every second, if the time changes, temperature also goes on changes in the element. Okay, in the element, given element. Let us analyze this the transient heat conduction. The analysis of transient heat, transient or unsteady state. It is also called as unsteady state heat flow can be done by using the following methods. Some of the methods he is mentioning here. Approximation or lumped capacity method. This is a very important method. We are deriving on equation. Analytical method, use of time temperature charts, production solution and graphical solution, numerical techniques. In that, only two methods we are using. That is the lumped system and the use of time temperature charts. That is, those charts are called as easilier charts. Easilier charts. Lumped capacity or the lumped parameter analysis. In this, the temperature of the solid changes with both the position and time. Means if the temperature of the element will be changing with the position as well as the time. If the physical size of the solid is very small, temperature gradient exists in the solid can be neglected. If the physical size is very small, the temperature change in the itself in the solid is negligible. That is, the variation of temperature with the position is neglected during the transient heat conduction. Hence, the temperature is a function of time only. Means the position of temperature with respect to the position, the temperature change with respect to position is neglected. Only the remaining one is only the temperature change with respect to time only. Okay, is known as lumped parameter analysis. Analysis of heat transfer under such assumptions means the temperature changes with respect to time only, not a position, is called as the lumped parameter analysis. Lumped parameter solution mainly used when there is no internal temperature gradient. Internal temperature gradient means within the any one solid. Like if you take the solid, the iron ball, if you take the iron ball, then the temperature within the iron ball will be neglected. Temperature change will be neglected. Only the temperature changes with respect to time is considered. Okay, temperature with respect to position is neglected. That type of the analysis is called as lumped parameter analysis. Okay. Okay. Lumped parameter solution mainly used when there is no internal temperature. We consider the same temperature throughout the depth of solid. Depth of solid means take anywhere the solid iron ball, anywhere there is the temperature is going to same. Expression for the temperature variation and the heat flow using the lumped parameter analysis. It's called as lumped system. This is very important derivation. Some cases they may ask in the examination. They may ask in the examination. Lot of times, whether you may ask the derivation or some cases you may ask this problems on this lumped parameters. Okay, using the lumped parameter analysis. Consider the solid. See, it's in this bath there is a fluid. Fluid means there may be the water, there may be the anything, any one fluid. Fluid means liquid. Okay. its temperature is T infinity. The convective heat transfer coefficient of this fluid may be the liquid here. He has not mentioned water. He has not mentioned any particular liquid. So that we are considering this as a fluid. Fluid will be having temperature T infinity and H is equal to the convective heat transfer coefficient. There is a irregular solid is there. Irregular. The boundary of this solid is not a fixed one. Irregular. Irregular. So that volume of the solid is V and area of the surface of the solid is the surface area of the solid is A, and K is the thermal conductivity of the solid, rho is the density of the solid, the C the specific heat of the solid, and then T is the uniform initial temperature of the solid, Ti, and then T is the temperature of the solid at a given time interval. And if the solid is suddenly immersed in the well-stirred fluid, this fluid is well stirred because the fluid temperature is maintained constant T infinity, so that after stirring takes place, the temperature of the fluid gets the uniform. Okay, time T is equal to 0. Heat transfer between the solid and the fluid takes place by convection, because you see here the convective heat transfer coefficient of the fluid means the fluid may be the liquid form. He has not mentioned any particular, so that we are considering a fluid in general. Okay, assuming temperature is a function of time only, we have the rate of heat flow into the solid by solid of volume V. This solid of volume V, rate of heat flow into this is equal to rate of increase in internal energy. If the rate of transfer of heat flow into the volume V is equal to the rate of increase in the internal energy of this solid, rate of heat transfer into this solid is equal to the rate of increase in the internal energy of the solid volume V. This is a very important relationship for this, the derivation. Okay, for this derivation. You see here, rate of heat flow suddenly, as I said, this the occurring due to the convective mode of heat transfer. Convective mode of heat transfer from the fluid of temperature T infinity, and the the any other fluid, it's also having convective heat transfer coefficient, that is the H into A, area of the fluid, into T infinity minus T. Minus T is the temperature of the solid. It changes with respect to time, is equal to mass into specific heat into temperature of the solid with respect to time. Increase in the internal energy is nothing but the mcp delta T. Mcp delta T is nothing but the mass into mass of the solid into C is the specific heat of the solid, dt by dx. The temperature of the solid changes with respect to time is called as dt, differentiation of temperature capital T, temperature with respect to differentiation of time. HA is the convective mode of heat transfer into area of the beaker, area of the beaker which is containing the fluid of temperature T infinity, right? T infinity minus T, M is equal to density, mass is equal to density into volume. Okay, density is equal to mass by volume. You are studied in the fluid mechanics. You recall the funda. This is a the fluid properties in that in that chapter, fluid properties in the third semester. You are studied this in the third semester fluid mechanics subject. That is the fluid properties chapter. In the any textbook you refer it, density is equal to mass by volume. It is a unit is kg per meter cube. You are studied this. The hence, by taking the equation from that the chapter, mass is equal to density into volume, I am substituting to in this equation. Okay, dt by dx, I'll send this HA rho V T infinity minus T is equal to minus I'll take this side, T minus T infinity, it becomes HA rho VC dt by T infinity, T minus T infinity is equal to minus HA rho V dt. Integrating the above expression, this expression, integrating with respect to dt by T minus T infinity minus HA rho V. Rho V is the mass into C into dt. Log of T minus T infinity. If you 1 by x is equal to log of x. Okay, integration of 1 by x is equal to log of x. You recall the equations. Minus HA rho V C is T plus it is a integration constant C1. If you call this as equation 1, applying the initial boundary condition, T is equal to 0. At 0 temperature, T is equal to Ti. Means the temperature of the solid is initial temperature of the solid. Ti is nothing but the initial temperature. If you substitute that the boundary conditions in the above equation, you will get the log of Ti minus T infinity. Ti is the initial temperature at a temperature time is equal to 0. Time T is equal to 0. The lowercase t. Ti minus T infinity is equal to minus HA rho Vc into the T is equal to 0. T is equal to 0. I am substituting in the equation 1 plus C1. It implies that the log of Ti minus T infinity is equal to C1. Substituting C1 in the above equation 1, log of 1 minus infinity T infinity is equal to minus HAT rho Vc plus log of Ti minus T infinity. By rearranging these equations into the different form, T1 minus T infinity minus of, if you bring this to this side, log of minus Ti minus T infinity is equal to minus HAT divided by rho Vc. Log of A minus log of B from the equation of the second PUC equation, or maybe you are studied in the first PUC or second PUC, these equations. Log of A minus B is equal to log of A by B. Log of A plus B is the log of A minus B. Log of A minus log of B is equal to log of A by B. That equation, by using that equation, log of E natural log T minus T infinity divided by Ti minus T infinity is equal to minus H A T rho Vc. T minus T infinity, if you bring this the natural log to the right hand side, it becomes a e to the power of exponential power of minus HAT divided by rho Vc. It becomes the equation 2. I am calling this as a equation 2. This is a temperature variation expression for one-dimensional transient heat conduction. This is a temperature distribution for the one-dimensional transient heat conduction. The exponent from the minus HA delta HAT rho Vc can be arranged as HAT rho Vc is equal to HA V VKT rho V square C. By here simple multiplying dividing by VKA. From here VKA multiply and divide by VKA. V is equal to A into L naught. Okay, V is equal to A into L naught. By using that, V is equal to A into L naught. Therefore, AT rho Vc is equal to H A into A into V. A into V is the rho LC A square K T divided by Ka rho A square LC square. If you simplify this, you will get the HL by K into K by rho C 1 by LC square. It is HLC by K alpha. K by rho C phi is nothing but the thermal diffusivity of the solid. Thermal diffusivity of the solid alpha divided by 1 by LC square. HLC by K into alpha T LC square. LC is the characteristics length of the solid, which is equal to the ratio of the volume of the solid to its surface area, V by A. The term HLC by K, the characteristic length LC is called as Biot number, Bi, suffix V, I, Biot number. Alpha T by LC square is called as Fourier number. Therefore, HAT rho AVC, the term becomes is equal to the Biot number, it's a Fourier number. If you substitute this Biot number and Fourier number equation into the temperature distribution of one-dimensional transient heat conduction temperature distribution equation, it becomes T minus T infinity minus divided by Ti minus T infinity is equal to e to the power of minus Bi Biot number into Fourier number. This equation becomes 3. Instantaneous heat flow is equal to Qi is equal to rho V C dt by d mc. Mc is nothing but the m is the rho V C dt by dt. From equation 2, we'll get the T minus T infinity. From equation 2 is from this equation. Okay. If you send this side and the rearranging this, you'll get the T is equal to T infinity Ti minus T infinity e to the power of minus Hat divided by rho Vc. Again, if you simplify this, you'll get the substitute this in the above equation and differentiate this, you'll get the Q is equal to rho Vc dt d by dt t into T infinity plus Ti minus T infinity e to the power of this term minus Hat rho Vc. By simplifying this, the differentiation of this term with respect to time, T infinity is 0 plus Ti minus T infinity minus Ha rho Vc e to the power of minus Hat divided by EVC. Okay. Qi is equal to minus Ha Ti minus T infinity e to the power of minus Hat rho Av. It is equal to the Qi is equal to minus Ha Ti minus T infinity e to the power of, this is nothing but the Biot number into Fourier number. Biot number into Fourier number. Okay. This expression for the instantaneous heat flow, unit for instantaneous heat flow rate is watt. Okay. Now, by simplifying all the things, because you see here simplification, you may go wrong. Just you cancel this rho Vc gets cancels. Remaining is minus Ha is here, minus Ti minus T infinity. This term is as it is. Okay. Heat flow rate. Heat flow is nothing but the loss or gain. Both there may be loss, there may be gain. Is obtained by integrating the equation 4 over interval 0 to t. Q1 is equal to integration of 1 to 2 Qi into dt. Okay. Is equal to 0 to t minus Ha Ti minus T infinity e to the power of this term into dt. It's equal to the minus Ha Ti minus T infinity e to the power of Hat rho Av divided by minus Ha divided by rho Vc. This is okay. This becomes, if you simplify this, you will get this is the simple simplification. You will get this Qt is equal to rho Vc Ti minus T infinity e to the power of Bi Biot number into Fourier number minus 1 joules. This is the temperature total heat Qt. Okay. Characteristic length of the different types of objects. LC. Rectangular slab, volume by surface area, V by A. V is A into L, area is 2A, A into A, 2 surface area, L by 2. It becomes, simplify this, A get cancels, L by 2. It becomes, okay. Cylinder, LC is equal to V by A. Cylinder 4 pi r square into L is the volume, pi r L is the surface area. It becomes a R. The sphere, characteristic length is V by A. V is 4 by 3 pi r cube divided by area is 4 pi r square is the area of the sphere. If you simplify this r cube divided by r square gets cancels, when the remaining is r 4 get cancels, remaining is 3 pi gets cancels. It becomes the r by 3. Cube, it is a LC is L cube divided by 6 L square divided by is equal to 6 by L. The time required for the lumped system to reach the average temperature. Reach the average temperature means initial temperature Ti is equal to 0 plus T infinity divided by 2. T infinity is the temperature of the fluid, Ti is the temperature of the solid. Initial temperature at the T temperature time is equal to 0. Time is equal to 0 and T infinity is the temperature of the fluid. If you divide that, you will get the average temperature. We know that T minus T infinity temperature distribution divided by Ti minus T infinity is equal to e to the power of minus HAT divided by rho Vc. When T is equal to Ti plus T infinity by 2, the above equation becomes, this equation becomes Ti minus T infinity by 2 minus divided by T infinity T1 minus T infinity to the power of this term. Here Ti gets cancels, both will get cancels. 1 by half, it is equal to e to the power of exponential to the power of minus HA divided by rho Vc. Taking the log on both sides, you will get the T is equal to 0.6932 rho Vc divided by HA. The time, the thermal time constant, the Tc is equal to rho Vc by HA as the dimensions of time. It's called as thermal time constant. It is its values is indicates the rate of the response of the sudden change in the environmental temperature. Means if there is any sudden temperature change, it will indicate, okay, how fast the body will respond to the change in the environmental temperature. Significance of Biot number. Significance of Biot number. Biot number is given by Bi is equal to H LC by K. Yeah, LC is the nothing but the characteristic length. Okay, LC by K, Ka, conduction thermal resistance, L by Ka, HA, convection thermal resistance. Means conduction resistance divided by convection resistance. Biot number is the ratio of internal resistance due to the conduction to the surface resistance due to the convection. Means the internal resistance due to conduction to the surface resistance to the convection. If Bi, Biot number is 1, effectiveness is unity. Yes, there is no use of fins as it will not increase the heat flow. Biot number is greater than 1, effectiveness is less than 1, there is a adverse effect on the heat flow and the fin works as a insulator. If Biot number is less than 1, effectiveness is greater than unity, effectiveness is greater than unity, it is called as most desirable place, because the Biot number is not 1 also not desirable. Biot number is greater than 1 also, it is not desirable. Only the Biot number is less than 1, it is the most desirable for the using the fin. Fourier number. Like any other dimensionless number, as we discussed in the previous case, that is the Biot number, the Fourier number also one of the dimensionless number. Fourier number is given by alpha t. Alpha t by LC square. Fourier number is defined as the ratio of the rate of heat conduction to the rate of thermal energy storage in the solid. Fourier number is the ratio of the rate of heat conduction to the rate of the thermal energy storage in the solid. Fourier number is equal to the Ka dt by L mc dt by dt. Okay, Ka dt by L divided by mc. M is nothing but the rho into V into C dt by d. If you simplify this, KAT, numerator, it will go to the denominator. These two things will get cancels. Remaining is rho A into LC. Rho A, V is A into LC. Okay, into C into LC. K by rho C into T by LC square is equal to alpha T by LC square. This is alpha. This whole thing is called as the K by rho Cp is nothing but the thermal diffusivity. It signifies that the degree of penetration of the heating or cooling effects through a solid, higher the Fourier number, deeper will be the penetration of heat into the solid during the given time. Means the Fourier number is more, then the more heat will be penetrated in the solid in the one-dimensional transient heat conduction. Okay, that is the meaning. If the Fourier number is less, the penetration of it is in the surfacial. Time constant and the response of the temperature measuring instruments. Measurement of temperature by the thermocouple is an important application of lumped capacity methods. The response of a thermocouple is defined as the time required to the thermocouple to attain the source temperature. You know that the temperature distribution as we derive T minus T infinity divided by Ti minus T infinity is equal to the e to the power of HAT divided by rho Vc. Larger quantity of rho VCHA is a faster the exponential term will approach to the zero. Then more rapid will be the response of the temperature measuring device. Okay, temperature measuring device. You see here, rapid will be response of if this is a faster, larger quantity of this term will be the response will be more. This capacity is achieved by increasing the value of H, by decreasing the wire diameter. Hence, a very thin wire is recommended to use the thermocouple to ensure the rapid response. Means if the more and more wire thickness decreases, then the response will be more. The term rho Vc by Ha is called as time constant. The time constant rho VHA is equal to Tc. T minus T infinity divided by Ti minus T infinity is equal to e to the power of the e to the power of B into Tc. T is equal to T is equal to Tc. We will get the uh, T minus T infinity divided by Ti minus T infinity e to the power of minus 1. It becomes the 0.368, 36.8. It is defined as the time required the temperature to change to reach the 36.8% of its final value in the response to a step change the temperature. That is the temperature difference would be the reducing 63%, 63.2%. Okay. Initial transient heat conduction using the Eslier and Grober charts. As I said, the analysis of transient heat conduction. Two methods. One is the lumped system analysis. Another one is by using the charts. That is the transient heat conduction charts or Eslier charts. They are represented. Some of the data after conducting the experiment, some of the data they expressed in terms of graphs. By using that graphs or the charts, we can analyze. We can solve some of the problems. Okay, Isolated charts are nothing but the analytical solution for the in the form of graph. Analytical solution in the form of graph. The charts are prepared taking the dimensionless temperature T naught by T infinity divided by Ti minus T infinity versus Fourier number for various values of Biot number. For solid different geometric shapes such as plates, cylinders, and spheres, these charts give the temperature history of the solids at its mid plane x is equal to 0. Temperature at other locations are worked out by correction factor. Correction factor. It can be read out from the charts. Okay.